Right, so yesterday we went through and described what climate is in terms of, is it the temperature, the average temperature, or spread out across seasonality, things like that. We also went through and described a simple model, okay, which when I say model, it's effectively just that one equation which describes the surface temperature of the Earth and how that surface temperature is dependent on the amount of solar radiation we get from the sun, the albedo or reflectivity of the planet as a whole, so that's reflecting off clouds and also reflecting off the surface, and then also this term called emissivity or absorptivity, which we assume are the same. So this is this epsilon term, and that's effectively the greenhouse gas effect. So how much of basically a black body does the atmosphere absorb of the long wave radiation that's going out into space. So today we're going to talk, well, I'm going to talk, you're going to pay attention. We're going to talk about what the evidence for these past changes is, okay? And then we're going to start looking at some of the longer term changes of Earth's climate, bringing in some of the carbon cycle, so the emissivity term in that equation. So looking at how that has changed potentially through time and what might have caused those changes. So if we start off with how we know the climate's changed in the past, so we can't measure directly the past climate. So we might want to know the average temperature of Scotland over 100,000 years. We might want to know the average temperature of, say, the continent Gondwana, like hundreds of millions of years ago. And we can't measure that directly because no one was there with a thermometer at the time and a notebook writing down the temperature. So we do have records of temperature that are hundreds of years long, and I think I'll show you one of those in a bit, because humans have been writing down how hot it was for hundreds of years. But if we want to go further into the past, then we need some indirect measure of temperature or indirect measure of some climate parameter. So temperature, precipitation, salinity of the ocean. And the way we do that is with these things called proxies. So just like when you vote in an election, you can vote by proxy, which is where someone else votes for you. You can record the climate by proxy by using something that is not temperature, okay, to act as if it were temperature. So various environmental parameters, things that are recorded in the sedimentary record or the other kind of climate archives, which we'll go through, acts as basically a proxy for that. Okay, and we'll go through and explain that in a bit more detail. Okay, so these things are broadly into three categories. So things, lithological information. So you guys went to Pease Bay, look at some sandstones. At least I know some of you did because I was there. And those sandstones look like they were deposited in a desert environment. So we could use that rock evidence to tell us something about the climate of that place in the past. Okay, it was hot and dry, maybe. Okay, quite qualitative, not very quantitative. We can't say how hot. Biological information. So fossils, we can find those in the geological record, all different kinds, and different animals, different plants tend to live in different environments. Okay, so if we find crocodile fossils, we know that kind of reptiles, cold-blooded, so they don't tend to live in kind of Arctic environments. So if we find those crocodile fossils in Antarctica or in Greenland, which we do, that tells us that in the past those regions were probably quite warmer. And we'll go over some more examples of that. And then this last class, chemical information. So we can use the chemical composition and also the isotopic composition. And if you don't understand what that means, then that doesn't matter. We'll come on to that in this course in a bit, and there are other courses in the future as well. But the chemical and isotopic composition of stuff that forms in environments of the past is quite often dependent on environmental conditions. So the temperature might affect the ratio of different elements that get incorporated into the shells of fossils and things like that. So some climate sensitive rock types. So this is the lithological class. So if you find fossil coral reefs, Okay, that's usually indicative of that region being in a warm environment. You can get cold water coral reefs, so that the principle of uniformitarianism, you guys covered that in Earth Dynamics. This is the idea that the present is the key to the past. Doesn't necessarily hold true through all of geological time, so maybe coral reefs in the past might have been a bit different, so they could have maybe tolerated colder water. But broadly speaking, we can take these kind of environments that these rocks are forming in today, so corals tend to be kind of warm, wet environments. Aeolian sands tend to be in dry, hot, arid environments. If we find glacial deposits, so glacial tills, drop stones in lake deposits, that tends to be formed in very cold environments. And evaporites, things like salt deposits, that only happens when it's hot. So we can find these rocks in the past, we know how old they are, that gives us a point back in time where we can say, right, this is what the climate was like. Just as kind of like a caveat to that is that if you're going to reconstruct the climate based on any proxy evidence, this applies for rock evidence, lithological evidence, but also the biological and the chemical ones, it matters where you define that. So for instance, this is a map of all of the different paleoclimate zones, or the climatic zones across Earth now. Okay? So if we went to the Sahara, which is here, the Sahara, for those that are not so knowledgeable about Africa, I guess there's a big desert there. And you were to look at the rocks that are forming there now, you'd think, it's very hot and arid. But if you were then to go to the coast of Brazil, and you say, well, there's kind of swampy coal deposits being formed there right now. There's maybe some coral reefs offshore. You think, it's kind of what's wet. If you were then to go to northern Canada, okay, in the Rockies, let's go to the Rockies, these purple regions here, you'd find glacial deposits, all at the same time, okay, so all in the modern, and you'd interpret completely different climates from those, because climate is not the same over the whole Earth. It's different depending on where you are. So if you're looking at finding, if you find glacial deposits in rocks of, I don't know, Ordovician age, that doesn't necessarily mean the globe was warmer then. Okay? It just might mean that you're looking at a rock that formed near the poles. Okay, so knowing the paleogeography of your paleoclimate reconstruction is important because it provides the context which you can then take your paleotemperature or paleoprecipitation proxy and interpret the wider global climate. So another kind of line of evidence is extracted from deep sea sediments. So this is the ship, the Marianne Dufresne. There are lots of ships like her that are specifically tasked with dropping objects like this. So this is basically a long tube with an enormous lead weight on the end of it, and you drop that onto the seafloor, and it basically takes a core of sediment. And this is one of those cores with some scientists working on it, extracting the sediment. And this is a close-up of that, so you can see layers of sediment. So this is kind of should be vertically, but it wouldn't fit in the thing. So those layers of sediment are recording the environmental conditions at the time. Okay, so if they're at the bottom of the ocean, they're recording the conditions at the bottom of the ocean. But they're also recording the conditions at the sea surface, because deep sea sediments are quite often full of microfossils. Okay, so like this is a microfossil. This is a benthic foraminifera, which lives on the bottom. But there are ones that live in the surface, so marine plankton. The fossils of marine plankton might tell us something about the sea surface conditions back through time. So these are those kind of things. So these are the kind of organisms that live in the upper water column. So this is part of a coccolithophore, which is one of the most abundant marine planktons. We've got at the top up here, this is a foraminifera, which is kind of basically a kind of single-celled animal thing that likes to photosynthesize. We also have diatoms and radiolaria, which also kind of get preserved in sediments. So what we can do is, one of the things that we can do is just look at the fossils that are there and see what kind of environments they like to live in. So this is an example. This is Neogloboquadrina pachyderma, which is a type of planktonic, so lives in the surface ocean animal, foraminifera, and it has two varieties. So it has a dextral and a sinstral variety, and all that means is that the shell coils. See, this one coils this way, and this one coils the other way, lefty righty. Okay, and it turns out that the dextral, so that the one that coils to the right, likes to live in warm water, and the other one, the lefty spirally one, lives in cold water. So if you were to find some deep sea sediment, you could count how many of each one of those you had, and what you could do is you could look at this kind of graph here, then look at the ratio of lefties to righties, okay, and then you could read off what the temperature was. Okay, so if it's near 100%, then you know it's probably warmer than 16 degrees. Okay, so this is quite a nice example of a proxy calibration, which is very sensitive from 4 degrees to 16 degrees. So you can see you could maybe, if you got 50%, you'd read off and it was about this temperature, around 9 to 11. But once you get above a certain, once you've basically got into warm water, you can't tell how warm it is. So your proxy calibration basically has saturated. It's reached a threshold by which it's no longer useful. So that's not a problem. You just have to find a different proxy. So one of the things about proxies is that they're not universally kind of applicable. Okay, they're quite often limited to either a very specific geographical region or a specific climate range. Okay. So yeah, so like I say, so not all proxies are good proxies. So if you wanted to reconstruct, say, temperature, one of the things you might use is the oxygen isotope composition. So don't worry about what all these squiggly symbols here mean. But this is just oxygen has got a number of isotopes, oxygen 16, 17, and 18. And the ratio of oxygen 16 to oxygen 18 is dependent on a bunch of environmental parameters. Unfortunately, if you measured that, that might change with temperature, which would be great if that's what you wanted to know, but it might also be affected by other things. So it might be affected by the amount of global ice volume, by the amount of salinity, by the calcification rate, all kinds of things. So your proxy is not only an indirect measure of the climate parameter you're wanting to measure, it's also an indirect measure of other things as well. So you can get quite a confused interpretation sometimes with these proxies. Another problem is seasonal bias. So if you're using those fossil planktonic forams to tell you about temperature, that tells you maybe about the temperature when they were living in the water, but they might not live in the water all year round. So there might be preferentially more plankton in the water in spring and summer, but not in winter. So that means that you won't have any fossils that are representative of the winter temperature, which then means that your proxy will be biased towards summer temperature. So if you then interpret the ratio of lefties to righties and say, oh, that's the average annual temperature, it's not. Okay, it's some mixture of mostly summer temperature with maybe some spring temperature, some autumn temperature as well. Okay, so you need to think about things like seasonal bias. And then also this problem, which is particularly problematic with lithological or geological proxies, that when you go really far back into geological time, maybe some of these relationships between the environment and the mode of deposition do change. Okay? So the example there would be the rocks that we saw at Siccar Point. We saw that they look like desert sandstones, no plant material in them, so it didn't look like it was like a wet environment at all, quite dry. But there were no land plants hadn't evolved by then. So that might also affect what we see being preserved in the rock record. Okay? So uniformitarianism is not so uniform. So this is a little primer about oxygen isotopes. So I'm not going to go through this now. I think you've got it in your handout if you're interested in it. We will go over this many more times in many more courses. If you want to, if you subscribe to my YouTube channel, there's lots of videos on this. if you really have nothing better to do at the weekend. I'll talk a little bit about now another type of record, which is the ice. So ice cores are basically drilled down through the large ice sheets in Antarctica and Greenland, sometimes in continental ice caps as well. So these are where you get basically snow falling on the top of the ice sheet, and you can see that there are layers built up here, and basically you get almost a layer every year as you get more snow deposited in winter. Okay, and so these are, you drill through them, and you either drill through by, usually by coring it out. Sometimes they drill by melting the ice, but that then ruins the sample for some applications. So there are a number of these cores from Greenland and Antarctica. And if you look very closely, so this is a thin section of that ice. And you can see the individual ice crystals kind of here. Okay? And in between those ice crystals, you also get little bubbles trapped. Okay? And this is because when snow falls, it's made of kind of lots of kind of interlocking crystals. So there's quite a lot of air in it. And as the snow gets compacted over time, as more snow gets added on top, those like spaces get trapped. Okay, so we get these are actually little samples of the atmosphere from when that snow fell. Okay, it's actually from a little bit later when the snow fell because for various reasons of diffusion through the porous snow. But you can think of this as, it's not, so these, we can go in and we can measure the CO2 concentration, all of the gas compositions of those pockets of air. So these are not proxies, because this actually is a direct measurement of the atmospheric composition back in time. But it's not just the gas we're interested in. We are also interested, we can actually measure the water ice itself. So the solid ice crystals, we can melt that out, and we can measure the oxygen isotopes of that and the hydrogen isotopes of that. And that tells us something about the temperature and relative humidity at the time of the snow formation, which is quite useful. So we get a local record of temperature. So also there's other things trapped in the ice. So we get little bits of dust, little bits of sea salt, which tell us something about how stormy it is, or how dry the planet is. So if it's very dry, the atmosphere tends to be more dusty, more dust gets blown up in the atmosphere. That ultimately gets deposited on your ice sheet. If it's very, very stormy, you get lots of sea spray blown up into the atmosphere, and you get more salt deposited in your ice. So you can use measures of these as proxies of the environmental conditions at the time, of storminess, of dryness, of local temperature. You can actually also measure the ice accumulation rate, so the thickness of each layer. So that the wetter the global climate is, the more it snows over ice sheets. So we can use that as a proxy for atmospheric humidity or atmospheric moisture transport. Something that you might be familiar with are tree rings. So these are used to count how old the tree is. So you get a layer grown every year. So what scientists can do, we can basically drill into a tree with a corer and extract a core of the tree. We can count the rings and figure out how old it is. But we can also look at the thickness of each ring. Okay, so when it's depending on the type of tree and the local environment, when you have a warm year, okay, the tree grows more. Okay, so you have a thicker ring. When you have a very cold year, it tends to not grow so much, and you have a thin year. And it's not just temperature. So sometimes it could be because it's dry or it's wet. So again, this is one of these examples where it's quite hard to get temperature itself out of the proxy, because the thickness of the ring is dependent on temperature and humidity at the same time. Okay? But those things tend to be correlated with each other. So when it's warm, it tends to be wet. When it's cold, it tends to be dry. And what we can do is we can basically drill into trees that are currently living, and we can figure out what the relationship is between the instrumental temperature record that we have, because someone from the Met Office was measuring the temperature and the tree width, and we can then take that further back in time. So this is what we've got here. So the red line on here, so this is a study that was done up in St Andrews, but with data from Edinburgh. So the red line here is basically the summer temperature in Edinburgh. Okay? And you can see it's been a balmy kind of 13 degrees, toasty warm, taps aff, as they say, in Edinburgh. And then what they've done here is they're looking at the ring, the thickness of rings in the blue here of a series of trees. So you don't have to have one tree that's very, very old, because you can basically match up overlapping sections in terms of age based on the thin, thick, thin, thick, thin, thick ratio, like matching up a barcode. So you can build up this long, long history, and you can see that the blue line, which is based on the proxy reconstruction, quite nicely matches the red line. Okay, so this is a good example of validating a proxy, so checking it against some instrumental data before we apply it to the past. There should be, oh, there we are. Okay, so another example. So this is moving on to the more chemical type proxies. So corals. So this is, I think this is a picture of our head of department, Sandy Totope, over there. And you can see that he's drilling into a coral. And the coral, just like a tree, tends to grow in annual layers. But as well as growing in annual layers, we can maybe measure the thickness of those layers, but they're not usually related to the temperature, or because the growing conditions of the corals are usually quite complex. You do get quite different growth rates even on the same coral, the same place. But actually what does change with environmental conditions is the chemical composition of the coral. So it's forming this calcium carbonate skeleton. You can go and see some upstairs in the museum if you want to. There's some nice examples of corals up there. But the ratio of the element strontium to calcium in a coral is strongly dependent on the temperature in which that coral grew. So this is a study that I was involved with Sandy as well. And you can see that when we go from the kind of modern corals to the last glacial maximum, the amount of strontium in the coral has gone up. Okay, so you see that annoyingly the scale on proxy records is quite often flipped upside down. You see here the magnesium-calcium ratio goes from negative to positive, but the strontium-calcium goes from kind of low numbers to high numbers. So just be aware of that. That's quite a common feature of paleoclimate reconstructions, is that they tend to be plotted with whatever we think warm is up, irrespective of what the actual number of the proxy is. Okay? So this is some evidence that it was kind of colder in the past on that particular coral reef. So this is the kind of the philosophy of what we do. We want to know something, okay, some environmental parameter, and we want to know that through time. Okay, so we need to understand how our proxy works. Okay, to basically get these parameters here. So we need to basically understand in the modern how our proxy relates to environmental conditions, and that will then give us a reconstruction of temperature, ice volume, whatever. We also need to know when it happened. So we need to be able to figure out how old stuff is. So one way we can do that is by radiometric dating. So there's a long list of these things of over different timescales of maybe carbon-14 is good for maybe the last 50,000 years, but much older things you might need a different geochronometer, like lead isotopes might tell you, uranium lead dating would be able to tell you how old the Earth is, so very old timescales. And once again, all dating schemes are not good for measuring all kinds of things. So corals, great for radiocarbon or thorium, but you wouldn't be able to potassium argon date your coral. So the details of that are not so important, but just that we can use radiometric techniques to work out how old things are. We can also do this technique called wiggle matching, where if we have one climate record that we know how old it is. So for instance, maybe it was from an ice core, and some unfortunate PhD student had to count all of the layers in an ice core back to 400,000 years. So we know very accurately how old that ice core is. but then we might have a sediment core that doesn't have very, very well-defined layers. Okay? So we might then match the wiggle in one core to the wiggle in another core to basically to figure out how old our unknown ages are. Okay? So it's slightly more subjective, that mode of dating. Okay, so what we're going to do now is, so I've described some of the proxies that we use and the kind of the general philosophy of how we reconstruct past climates. So we're going to go on and discuss examples of this really long-term variability of the climate system. So we have large changes in temperature and environmental conditions over very long time frames. Okay? And as you move more to shorter timescales, the variability is different, but we're going to start long and old. Okay, so this is a proxy reconstruction of climate through the Phanerozoic. So since the Cambrian, which is over here, Cambrian, through to the Neogene, which is over here. And you can see, again, so what this is a proxy record using oxygen isotopes. So the details of how that work, not so important. But you can see, again, you see the scales being flipped upside down because we're like sneaky like that. But effectively, warm conditions with not a lot of ice on continents are up here. Cold conditions where lots of ice is on continents are down here. So isotopes recorded in marine sediments are usually a function of the temperature at which those sediments formed and also the amount of continental ice, okay, because that removes the light isotope onto land. But again, this is details that you can go through by subscribing to my YouTube channel, which is really boring, so don't do that. So one of the things we might want to ask is what is causing these large changes in temperature? So when it's cold, we have deposits that tend to be glacial deposits. We find them quite a lot, even at low latitudes. So one of these keys is that we don't just find them kind of just on the poles. They extend out over a wide paleogeographic area. So one theory is that if you grow an ice sheet, okay, if you have an ice sheet, that ice sheet is white. Okay? You've seen ice sheets before? They're white. And that means that if you have a very big ice sheet, that means a large surface area of the Earth is white, which means that it has a very high albedo, which means that it reflects light back out to space. And if you remember back to our kind of like equation, if we have a high albedo, that means we'll have a low temperature. So this is one of the ideas is if you make it easier to grow a large ice sheet, then you enable the albedo to go up, which means you cool the planet, which then gets you into this virtuous circle of making it colder, more ice, and then you have more albedo, and then colder, more ice, it carries on kind of. So what is it you need to initially promote that formation of a large ice sheet? Okay? So one of the theories is that if you have land situated over one of the poles, northern or southern hemisphere, that means that land is very cold, okay? Which means that it can accumulate ice. Okay? So if you don't have a continent over the poles, it'll be ocean, and you'll still get sea ice there, but it's very hard to build up a big amount of sea ice. Okay, it's very hard for it to stay there for a very long time. So one of the theories is that when continents were over the poles, that promoted glaciation, which led to an albedo feedback where it got cold, you have lots of ice, it reflects more sun out into space. So these are some examples of that. So this is the late Jurassic, when it was relatively warm, and you can kind of make out that the poles are relatively land-free. Okay? Whereas in the late Carboniferous, okay, so this is late Carboniferous in the UK is thought to be a time when the planet was very warm. So it's where all our coal deposits are from. Okay, we have lots of limestones deposited. So when you guys go to the Lake District, you'll see limestones with corals in. But actually, the globe at the time, the whole planet was much cooler. Okay, so during the Carboniferous, I think we are somewhere up here at the moment, depending on which part of Scotland you're in. But the whole planet was a lot colder at that time because these continents down here were covered with ice. But, okay, it's not always true. So you can look at other periods in time when we definitely have big continents over the poles. Okay, so this is the Eocene, and it's warm. So this is one of the times when we have fossil crocodiles in Antarctica in the Eocene. Okay, there's a bit of ice there, but the whole planet, this is one of the warmest times the planet's been during the Phanerozoic. So that's a bit odd. So that means that we kind of falsified our theory. So we can basically go through different periods in time and see, well, do we have large ice sheets? Well, yeah. Okay. So are the continents over the poles? Yeah. So that means that we support the hypothesis that the positions of the continents causes glaciation. But then we can go to other time periods. Okay. So we don't have ice sheets, but we do have continents in polar positions. So that falsifies the hypothesis. Okay. So it's a nice idea, and it probably does play a role in determining the global temperature, but it's not the main deal. It is possible, I mean, it's important, but it's not the only thing. Okay, so this is the equation that's important, and it's this term here, this alpha, this albedo, is what we're changing by promoting or inhibiting glaciation. So what about some of the other things of that? So we're going to think about the emissivity. So I'm kind of ignoring the power of the sun, okay, because there's no reason why the power of the sun would vary on that kind of timescale. It might get warmer and warmer through the whole of geological history, but not vary up and down on that long timescale of tens of millions of years, or hundreds of millions of years. So this is the carbon system, okay, and we'll see this in more detail later on in the course. So there's lots of carbon in the atmosphere, but there's even more carbon in the ocean. So these are kind of amounts in gigatons of carbon. So we have huge stocks of carbon in the ocean and in rocks. I mean, there's loads of carbon in rocks. Limestones, organic carbon in shales, loads of it. And these are some of the fluxes, so the exchanges between each of these different reservoirs of carbon held in rocks, the ocean. So you can see that there's a really big exchange of carbon between the atmosphere and the ocean, okay, up in and out of the ocean all the time. So you might think that those exchanges, the big exchanges, are the ones that will dominate the composition of the atmosphere. And that's kind of true, except over very, very long geological times, these fluxes are kind of in balance with each other. Whereas these very, very small fluxes, okay, over a very, very long period of time, can potentially count for a lot. Okay? And they're potentially not related to each other in terms of the amount of weathering of carbon from rocks into the atmosphere, or the deposition. They're not necessarily the amount of sediment formed might not be directly related. So these are some of these terms. So this is where we get onto the stuff that was given in the introductory video, which I'll try and whiz through a little quickly. So effectively, carbon dioxide in the atmosphere, okay, can react with rock. Okay, this actually happens mostly in soils. But the reaction of carbon dioxide mixes with water forms this acid which attacks rocks. And this is a really simplified chemical equation of rock. Okay, rock is not really that composition. That then takes stuff into the ocean. So this process of chemical weathering, okay, which is described in these equations here, takes carbon dioxide out of the atmosphere. Okay, so importantly, so the carbon dioxide reacts with water, forms carbonic acid, okay, then reacts to all of these other species here. So if you can have a reaction that takes rock and carbonic acid, that's effectively like a reaction of rock and carbon dioxide. So in the case of weathering of carbonate rocks, we take carbon dioxide, reacts it with water, reacts it with limestone, and we produce soluble ions that make their way into the ocean. So that removes carbon dioxide from the atmosphere. Same for silicate rocks. Okay? Weathering of silicate rock, carbon dioxide forms soluble ions that then go into the ocean. Okay? So both of those processes remove carbon dioxide from the atmosphere. Now, if that process goes on for long enough, that means that the concentration of these ions, calcium and bicarbonate, that will go up. Yeah? So that in the ocean, if you carry on weathering rocks, all of those products of weathering will find their way into the oceans and they will increase in concentration. And what that will do is that will promote the precipitation of calcium carbonate minerals. Okay, so if we have lots of calcium and lots of bicarbonate in the ocean, okay, it'll make it a lot easier for things like corals and shells to grow. We might even get inorganic precipitates. And unfortunately, that means that when this reaction happens, when we grow a coral or form a shell, okay, in the ocean, that actually releases carbon dioxide back into the environment and ultimately back into the atmosphere. So if you look at these equations in detail now, if you weather calcium carbonate, if you weather limestone, that removes carbon dioxide from the atmosphere. But if that stuff gets into the ocean and over a long enough time scale, this equation is balanced by this equation. Okay, so on short time scales, if you have a sudden increase in weathering, that might draw down CO2, but if you leave it for long enough over time, we'll precipitate calcium carbonate and give that carbon dioxide back up to the atmosphere. So that doesn't, over very long time scales, it doesn't change carbon dioxide in the atmosphere. If you look at silicate rocks, however, okay, if you look at the equations here, the weathering of 1 mole of silicate rocks removes 2 moles of CO2. Okay, whereas the precipitation of 1 mole of that calcium from that silicate rock back into calcium carbonate only releases 1 mole of carbon dioxide back into the environment. So weathering of silicate rocks will lower atmospheric CO2, but over a long time scale, that CO2 will stay removed from the atmosphere. Okay, it won't go back up again. So weathering of silicate rocks will remove carbon dioxide from the atmosphere. Okay, so that will lower the greenhouse effect, that will lower the emissivity of the atmosphere, and temperature should then go down. So what affects weathering? Okay, so weathering, just like any chemical reaction, goes faster when it's hot. Okay, so in a warm climate, we'll have more chemical weathering. Okay, and that means we'll have, and we also have, when in a warm climate, it tends to be wetter, more precipitation. So when you've got more warm, more wet, you'll also have more chemical weathering. Okay, because there'll be more water to do that weathering of the rocks. When it's warm and wet, you also get more vegetation. Okay, and the more vegetation you get, the more active your soil is. The more active your soil is, you get more humic acids and carbonic acids in the soil. That also increases chemical weathering. So when it's hot, wet, you get more chemical weathering. That means that you get more carbon dioxide removed from the atmosphere. Okay? Ooh. Removed from the atmosphere. And then that cools the climate because of our equation. So this is an example of a negative feedback. Okay? So if we have a warm climate, okay, we get increased temperature, we get more weathering. That removes more CO2 from the atmosphere and it makes the climate cooler. So it basically counteracts the initial forcing. Okay? So that's if the change in weathering is caused by the climate, it counteracts to basically moderate the change in the climate. So actually over the very long geological timescales, weathering acts as a kind of like a nanny to the climate. It keeps it in check. If it gets too warm, we have lots of weathering and that cools us down again. If it gets too cold, weathering slows down a bit, allowing the CO2 to build up in the atmosphere. So it acts as a moderator. So it can't explain the changes in climate, but it can explain why they don't kind of shoot off the graph to ridiculously hot, ridiculously cold. So one of the things we've got to think about is what else might change the climate. Okay? So if it's not the climate affecting weathering, weathering might affect it in some other way, as long as the change in weathering is not caused initially by climate change. The other thing is the other kind of counter to taking carbon dioxide out, it's putting it back in the atmosphere. So carbon dioxide on long geological timescales comes from volcanoes. Okay? Over short timescales, it can move in and out of other parts of the carbon cycle, through the oceans, biosphere, through us burning fossil fuels. But over long timescales, it comes from volcanoes. So the amount of volcanism has changed in the past. So when C4 spreading was faster in the past, we had more volcanoes, okay, because this process was going on faster, and that meant that this more subduction, therefore more outgassing. So you've done the magnetic stripes of how we measure C4 spreading in Earth dynamics. Maybe one person nods, that means you've all done it. So okay. So if we can measure how fast or how much volcanism there's been in the past from the proxy of C4 spreading, then we might be able to see how much extra CO2 is in the atmosphere, and that might tell us about these climate changes. Another thing that maybe increasing the rate of plate tectonics could affect climate is that if we have lots of mountain building, okay, that forms lots of steep slopes on mountainsides, which means we have lots of physical erosion. And this is basically a schematic of a rock. If you have lots of physical erosion, you break it into smaller bits of rock. Yeah. And that means that the surface area of your rock has then gone up exponentially. And weathering is a function of surface area, because it's a chemical reaction from a solid to a liquid. So that means if you have lots of physical erosion, lots of like uplift of mountains and formation of sediments, that means that your chemical weathering will also go up. So the idea is that you uplift a mountain, you get all of these kind of geography happens. Geography teachers go, ooh, mass wasting, landslips, and they go crazy. And that causes the rocks to be broken up into smaller fragments, and that in itself could change the weathering rate, increase the weathering, and cool the planet. So this is a forcing, not a feedback, because it's not, the initial change in weathering is not being driven by a climate change, it's being driven by this mountain uplift. Okay, so this is the idea here. So at this time, when Pangaea was kind of like forming in the Permian, I think. Yeah, early Permian. Oh, yes, I remember that. You can see there's this big mountain belt here. Okay, so it's uplifting, it's forming lots of easily erodible products, and also critically, it's uplifting near the equator. In this place where lots of weathering can happen because it's warm, because it's wet. If you formed a mountain belt on the North Pole, nothing's going to happen. Okay? You'd form lots of sand, the sand would go in the ocean, there would be no weathering. So these might explain some of these periods here, where we've got Permian glaciation, might be due to that uplift causing cooling through increased weathering, drawing CO2 out of the atmosphere. Similarly, maybe this guy here might be. Okay, we're going to think now about what about this change? Why does it get warmer towards the end of the Cretaceous? So this is that time. So one thing that's kind of a little bit different from the planet now, you can see there's loads of these warm, these shallow seas. Yeah. So one of the reasons for that is that sea level is higher at this time. Okay, so this is trying to explain this uppiness here. It's warmer at this time as well, so it's warmer, sea level is higher. How can these things be related? So if you look at a sea level curve, so this is a really cartoony schematic of a sea level curve. So during 80 million years ago, the Cretaceous, sea level was maybe almost 200 meters higher than it is present. Okay? So that can't be due to us melting all of the ice. Okay, so now if we melted all of the ice on Antarctica and Greenland, sea level would only go up by about 50 to 60 meters. Okay, which would be catastrophic, it would be very bad for us. But it can't be, sea level in the Cretaceous can't be this high because all of the ice was melted at that time. There must be some other reason. And the reason is, at this time, the ocean, the Atlantic Ocean, was first starting to form. Okay? So when we had a very, very young mid-ocean ridge that had just started to spread apart at this time. And that basically formed this huge mountain range at the bottom of the ocean, okay, which basically pushes up sea level. We've basically displaced a huge amount of the ocean and put a mid-ocean ridge there, which means that explains why we've got this really high sea level at this time, but also that would cause there to be much more volcanism at this time. More CO2 coming out, and that explains the warming. So this is this idea here that if this high sea level, this is spreading very fast ridge, we get a less space in the ocean, so the ocean goes onto the land. So in this case, we're using the sea level rise as a proxy for this mid-ocean ridge spreading event. So we also see this in the data of the magnetic lines. Okay, so yeah, so this is the reasons for that sea level change. So to summarize today's lecture, we've got the stuff from the proxies, but then when we're looking at long-term climate changes, okay, so these are things that take tens to hundreds of millions of years, what's driving climate is a balance between weathering and volcanic CO2 from basically the rate of plate tectonics. And that's basically the balance between those two fluxes of the carbon dioxide, so looking at the emissivity term in the atmosphere, that's what's driving climate. There will be additional effects, such as the position of continents affecting the albedo feedback, but over long time scales, it's the CO2 in the atmosphere which is really, really important. So